right, so happy to have Daniel give his second talk on Nonabelian Hodge theory.
Thank you. It's nice to be back. So before I begin, maybe let me encourage you all to ask lots of questions, and also let me say, so the four talks I'm giving are thematically dependent on one another, but mathematically independent. So if you get lost on one of them, you should expect that you'll be able to pick up the thread again on the next one. So don't fear if some of this, if you like number theory more than algebraic geometry or more than complex geometry, there will be a lot of number theory in the next talk. So, yeah. Okay. Right. So last time we talked about some kind of non-abelian analog of monodromy representations and the Riemann-Hilbert correspondence. So this time I want to talk about the non-abelian analog of what Elam told us about. So the story of Hodge structures and variations of Hodge structures to some extent, and then I'll kind of describe things as some kind of package, and mostly focus on how you can use that package to say kind of concrete things about local systems on algebraic varieties. So at least some of the motivation here comes from a conjecture some of you may have heard of, which is the Hodge conjecture. So Sasha, in his talk yesterday, told us about some motivation coming from an analog of the Tate conjecture, which I'll talk more about in the next talk. But I want to now remind you what the Hodge conjecture says, and then describe a non-abelian variant, and then set up enough kind of technology to massage the statement of the non-abelian variant so it looks a lot like the usual Hodge conjecture. Okay, so what does the Hodge conjecture say? X is a smooth projective variety over C, and then just like Sasha told us, there's a cycle class map from the group of linear combinations of codimension I subvarieties of X, so codimension I cycles on X, tensored with Q, to, since we're over C, we might as well work with singular cohomology of X with, I'm going to put Q coefficients here so I can receive a map from Q vector space. And then there's a little maneuver I'm going to do, which is mostly just to match up with what Sasha did, which I'll put an I here. Okay, so this is an almost meaningless object. What it means is that, well, this thing, when you tensor it with C, as Elon told us, has a Hodge filtration on it. It's a direct sum of some HPQs, and this means you subtract I from all the P's and Q's. Okay, so I'm going to write something that will make clear what I mean by that in a second. So the conjecture is that the image. So this is, I'm going to have cool. So this has image exactly the intersection of H2I x Q of I. Okay, and without this I here, you'd normally write HII of x, and with the I, what that becomes is H00 of x. Let me say C of I. So this means take the Durham this means you take the 2ith Durham cohomology of x, and then you take the I part, but because I put an I here, that becomes the 00 part. So that doesn't, you can ignore this I, just imagine that there's an I there. Okay, so let me tell you what the non-abelian analog is, and it's going to look totally different, and then I'm going to introduce a lot of stuff that will let us make these two things look the same. Okay, so what is the non-abelian version? So let me call this sort of grandiosely the non-abelian Hodge conjecture. Let's do the Simpson. So again, X is going to be a smooth projective variety over C. You can make the exact same conjecture I'm going to write for quasi-projective varieties, but let me not say anything about it. So then the statement is that a local system, any local system V on X, which underlies a Z, polarizable Z variation of Hodge structure, is of geometric origin. Sasha told us what geometric origin means. So let me just remind you, this means that there exists some dense open, yes, I should say Zariski open, since complex over the complex numbers of dense open U and X, such that V restricted to U is a sum end of Ri pi lower star C for pi y to U smooth and proper. Sorry, I don't know why I was trying to write vertically. Okay, so let me say a word about what underlies the ZVHS means. So here, when I say local system, I'm always going to be meaning complex local system. So the Z part means that complex local system comes from a Z local system by tensoring with C. VHS is what Elon explained. So when you tensor with O, there's some kind of filtration satisfying some properties. And then there's this extra word polarizable, which I'm not going to say much about. It just means that there's some kind of quadratic form on this ZVHS, which plays in a nice way with the Hodge filtration. It will be in the background of almost everything I say, but I won't. You can look it up on Wikipedia if you want to know. It won't be very important. Okay, so maybe you can kind of see that there's some kind of philosophical similarities between these two things. So being of geometric origin is supposed to be like being a cycle class, and being a ZVHS is supposed to be like living in the subspace of this vector space, but they don't really look that similar. So I want to describe some kind of structure on the space of local systems on X that lets you really make these things look extremely similar, and then give you some applications. Okay, so let me give you some analogy here. So the analogy you're supposed to have in mind here is that maybe H star X C is supposed to be analogous to the space of representation. Let me say HOM from I1 of X into GLRC to conjugation. So if you replace the C with a C star, this actually is literally a special case. So H star X C star, H1 X C star is the set of maps from pi 1 to C star, right? So GL1. So when maybe make a 1 here. So this is if you replace the C with the C star, you literally get GL1 here. Okay. So what Hodge theory tells you is that this vector space has some kind of let me make now of this an I again. This has some kind of decomposition, P plus Q equals I, into some HPQs, which, as Elon explained, have some kind of differential geometric interpretation, like cohomology of large powers of the Taylor differentials, the whole codimension bundle. Okay, and then Hodge theory is that there's some kind of isomorphism between these two complex vector spaces, which has a kind of highly transcendental nature. So the most of this talk will be devoted to explaining what lives here. Okay, and let me remark that there's another object which we don't really think of being so different from this one when we do complex geometry, but which does have a different nature here, which is, so you take the de Rham homology of X, and here the object is supposed to be modules with individual connections, so flat vector bundles on X. And here, of course, these two things are, we saw the Riemann-Hilbert correspondence, which told us that this rank R things here are an injection of rank R things here, but that is like a transcendental isomorphism. So when one does algebraic geometry, we'll see quite soon that these objects look really different. We'll put some kind of algebraic structure. Okay, so to tell you what goes here, let me make a definition. This is the definition of a Higgs bundle, and we've sort of seen an example. I'll recall it. So it's a pair E theta, where here E is a vector bundle on X, And theta, well, it looks kind of like a connection, but it's not. So let me write it down. So it's a map from E to E tensor omega 1x. Okay, so what's the difference between a connection, or this and a connection? So a connection satisfies this funny Leibniz rule, which was like, in particular, it was not O-linear. So this thing is O-linear. So remember, if you applied a connection to like f times s, you got s tensor df plus f times the connection. And if it was linear, that s tensor df term wouldn't be there. So here we've gotten rid of that s tensor df term. Okay, and then there's another condition, which is, so you can extend this to now like this, in maybe a not totally obvious way, but if you guess the answer, you'll guess correctly. And I want, sorry, this should be theta squared. I want this to be 0. So theta squared. Okay. So this is what a Higgs bundle is. So this is not quite the object that fits here, but it's almost right. Before I do tell you the object that fits here, let me give you an example of a Higgs bundle to show you you've seen some of these before. I want to give you 2 examples. So first of all, if E is any vector bundle, you can set theta to be 0. That's a perfectly good Higgs bundle. So a vector bundle is an example of a Higgs bundle. Okay, another example is if you have so we saw what a variation of Hodge structure is. So it's some kind of vector bundle E with a filtration and a connection. So this is a, I'm just going to write variation of Hodge structure. I think we only saw the definition of our RVHS. I'll say in a minute what a CVHS is, but you can think this is just some kind of, for now, just think it's an RVHS. So what did this mean? So this meant that when you took nabla and applied it to this, a member of this decreasing filtration, you ended up in one bigger piece, tensor omega 1x. And I claim from this data one can construct a Higgs bundle, and we saw this at the very end of Elong's talk. So let me just before I dive into that, let me maybe just make a word about this. So it's kind of hard to remember. Fi minus 1 is bigger than Fi, so you should think almost never will like the Gauss-Monod connection on a variation on like a geometric variation of preserve these Fi, right? Like that would mean that these are sub-representation. They give you sub-representations of the monodromy. And so some random monodromy representation probably is irreducible. There's no reason for it to have sub-representations. But this says they're almost preserved, right? The failure to be preserved by the connection is just off by 1. Okay, so how do you make a Higgs bundle out of this? So Elong more or less wrote down the formula. So what this does is this gives you a map from the direct sum of Fi mod Fi minus 1 to itself. Sorry, I plus 1. Tensor omega 1. Where what do you do? Well, you send Fi to the next term. Fi mod Fi plus 1 goes to Fi minus 1 tensor Fi minus 1 mod Fi. Okay, and so this is at least a map from a vector bundle to itself tensor omega, and the fact that it satisfies the second condition, that theta of theta is 0, it just comes from the flatness of nabla. So this was already a flat condition. So here this is, I'm gonna write ger nabla. Okay, so this is some example where from a flat bundle we've constructed some kind of Higgs bundle, and that should suggest maybe that there's some object here, there's some class of Higgs bundles that in some way come from flat bundles. And so that's what I want to describe now. So there's a sort of beautiful description of the class of Higgs bundles that do come from flat bundles. Let me make a definition. So this is slope and stability. Okay, so given a Higgs bundle E theta, I'm going to define its slope to be the degree divided by the rank. Okay, so here I've written degree sub h. What I mean there is you pick an ample divisor and use that to define a degree function, meaning you take C1 of E and come up with h the appropriate number of times. If you'll lose almost nothing in this talk by just thinking x is a curve, and this is just the usual notion of degrees. And I'm going to always suppress that kind of discussion from now on. And then I'm going to say, so this is the slope of a Higgs bundle. What you should think is that if E is a direct sum of line bundles, this is their average degree. Okay, and then you say that E theta is semi-stable. So here, semi is in parentheses because I'm going to define two things at once. So if for all sub-Higgs sheaves f theta prime inside of E theta, this is proper inclusion. So, okay, what does it mean to be a sub-Higgs sheaf? It just means a subsheaf of E which is preserved under theta. So f is sent to itself tensor omega. We have that the slope of f theta prime is less than, or in the semi case, less than or equal to the slope of E theta. Okay, so we're running over all subsheaves preserved by theta, and then we have this funny condition. Let's just think about what this means if theta is 0, and E is a direct sum of line bundles. So if theta is 0 and E is a direct sum of line bundles, it just means those line bundles all have the same degree. So it's saying there's no piece of E that's preserved by theta, and it is kind of surprisingly more positive thing. I think this is some condition that takes some getting used to, but for now I hope you just accept it. Okay, so now here's the theorem which tells you what goes in this question mark. So I'll erase the analogy and replace it with a theorem. And I will not be able to prove this theorem for you, it's quite deep, but one of the lessons of this talk is that you really can use it and get a handle on it. Like it's a very useful package. In the same way Hodge theory, typically one uses it as a package without sort of digging into the proofs, although not always, you can get a lot of mileage without digging into the proofs.
Here, just a question. Do you mean like strictly smaller or?
So there's a parentheses around this thing, so because I'm defining semi and semi-stable at the same time. So stable means strictly smaller, semi-stable means less than or equal to. Yeah.
So how is the definition of slope depend on the Higgs bundle structure?
Yeah, so the definition of the slope does not, but the definition of semi-stability does. It's a good question. Yeah, so here, the slope is, there's no reference to theta, but here you're only quantifying over f, which are preserved by theta. So for example, if there, so let me leave it at that. Yeah.
Anything irreducible is going to be stable, right? But
anything irreducible, yeah. So if
stable
E is, when you say irreducible, you mean like
it
if
gets in the category of Higgs bundles, right?
sure,
If you
that's true. That's true. Yeah.
But is there any example of something that's stable but not irreducible?
Stable but not irreducible. Sorry, maybe I don't know what irreducible means. Do you mean not a direct sum?
Just that there aren't like these like.
I mean, there's always sub. I think there's going to always be kind of
There's
sub
always-
objects. Yeah.
If the vector bundle is already stable without theta, then it is still stable.
Yeah, that's true. But vector bundles have sub bundles. Yeah, you can take E and tensor with like O of minus D for some D, and that will always be some sub bundle that's stable under theta. Subsheaf, sorry, not sub bundle. Okay, so here's the theorem, and this is, I'm going to try to summarize like a huge amount in this theorem. So maybe this starts with Narasimhan, Shabri, or some people like that, and continues with work of Kitchen, Corlette, Donaldson, Simpson, maybe other people too, and I'm going to put Mochizuki's name here. This is T. Mochizuki. Not because I'm going to write anything that's due to him, but just because the sort of the best version of this theorem is due to Mochizuki, or the quantum connective case. Okay, so I'm only going to state things in the smooth projective case, though. Smooth projective. So there's a bijection. So there is bijection, and I'm not going to tell you what it looks like because it's kind of complicated. I'll try to give you some sense of it. Between irreps of pi 1x, so complex irreducible representations of pi 1x, and stable Higgs bundles with vanishing Chern classes. Okay, so if you're on a curve, this just says the degree of the bundle is 0, plus this kind of funny stability conditions. So it has, this bijection has the following properties. So first of all, if rho from pi 1 of x to GLRC is unitary, meaning, for example, if factors is a unitary group in here, another way of saying that is that it's, the closure of the image is compact. Closure of the image is compact. Then here's an explicit description. So so first of all, you take the corresponding flat vector bundle. So this is a module with integral connection on X. So then the Higgs bundle is just the same vector bundle but with the 0 Higgs field. Okay, so what this says is that if you have a, well, this has, maybe let me finish writing this. So, and these are exactly the Higgs bundles corresponding to unitary representations. So this has a lot of content. So this is the part that's due to Nurseman-Seshadri. It says that if you put a stable bundle with vanishing Chern classes, then it has a unique flat connection on it with unitary monodromy. And then the rest of the content is that this bundle is stable. So if let me write it this way: if rho carries CVHS. Okay, so we don't quite know what this means, so let me kind of give a quick and dirty definition. So it means that rho plus rho bar carries an RVHS. So this is not the best way to define it, but this is equivalent to carrying a CVHS, and we do know what an RVHS is. So what do I mean by this? I mean that the associated flat bundle has a filtration which satisfies whatever relevant properties guarantee this hold. So what do I mean? I mean you take the conjugate representation that also has one of these good filtrations. There's some condition on a polarization. So then we know how to make a Higgs bundle out of such a thing. So what do you do? You take Gur E, so this associated graded thing I wrote over here, and you take the associated graded of the connection. So this is the corresponding Higgs bundle. Okay, and then there's some other useful properties that this correspondence has. So it's compatible with pullback, meaning if you have some map y to x, a representation of pi 1x, you get a representation of pi 1y. What's the corresponding Higgs bundle? If we pull back the Higgs bundle on x, you have to think a little bit about how to go from that to a Higgs bundle on y. But if you think about it first, you'll see how. So it's compatible with pullback, and it's also compatible with smooth, proper push forward. So again, it's if you have a Higgs bundle on y and y has a smooth proper map to x, you can push forward the vector bundle, that'll give you some, not totally obviously, some bundle on X, and then if you try to figure out how to make a Higgs field on it, you'll succeed. And so I'm only going to use this for finite étale push forward, and then it's sort of clear what to do. Okay. All right, so this is the theorem. It's a lot of data, and I claim that this data is analogous to the Hodge decomposition on cohomology. And it probably doesn't look like it, so I want to kind of convince you of that, and then convince you that you can kind of think about this Nonabelian Hodge conjecture as being a Nonabelian model of the Hodge conjecture. But before I do that, are there any questions about this very complicated statement? This if rho carries. So if rho carries a CVHS, which is some structure including a filtration, then the corresponding Higgs bundle is given by just taking the associated grid with the filtration and using the Higgs field coming from Griffith's transversality. So the fact that this nabla only bumps the filtration up by 1 means that you get some map from the graded pieces, from the ith graded piece to the I minus first graded piece for all I. That goes together into a Higgs field. Just like I wrote over there. Does that answer your question? Yeah.
And also, what is the I in the statement?
Where is it?
I didn't see I.
For all I. Yeah, so for all I. Yeah, all the term classes. Yeah.
For the first one, is it clear why all the term classes have to vanish?
It is not totally clear. So I think, so that's true for any bundle of flat connections, in fact. And one way to see it is that you can construct the Chern classes out of the Atiyah class. You know what the Atiyah class? Okay, there's some kind of weird class from which you can construct it's the obstruction. It's basically the obstruction to the existence of a flat connection on E. Okay, but the fact that you can construct all the Chern classes from the obstruction to the existence of a flat connection means that if there is no obstruction, all the Chern classes vanish. I don't feel like I really answered your question there because I didn't tell you what the Atiyah class is, but that's at least one sort of quick and dirty way to see that just having a flat bundle already implies that all the CI are zero.
But is the converse also true? The Chern class vanishes?
No, not in general. You can already see that on a Riemann surface. So if you take P1 and take O of 1 plus O of minus 1, that doesn't carry a flat connection. Yeah.
Practice. How hard is it to check stability?
And not very hard, actually, in my opinion. I mean, yeah. So the fact that you're quantifying only over things preserved by data is typically a very strong condition. So for example, maybe it's too cheap to take the case with it. So let's suppose E has rank 2, and it's like a direct sum of two line bundles, L and M, and the Higgs field goes from L to M tensor omega. All it's saying is that L has positive degree and M has negative. That's all you do. If the Higgs field is non-zero.
So just in these two examples, when you pass from rho to Higgs bundle, you always pass through this MIC.
Yeah,
That's always the case. Like
I mean, is it always the case? I mean, there's an equivalence of categories between the rows and the MICs. So.
But like, I mean,
No,
the
but
way
the
how
proof
you,
does. So yeah, so the way this is all I'm gonna say about the proof is, so you start, right, you have to go from a flat bundle to a Higgs bundle and vice versa, and the way you do it is by passing through a category called harmonic bundles, which are bundles with a very certain special kind of metric. Basically you write down some PDE that the metric has to satisfy in terms of your flat connection or in terms of your Higgs field, and once you have that thing, you extract out of it by looking at either the del or del bar term of the corresponding, like the connection corresponding to the metric, a Higgs field or a flat connection. That's all I want to say. Thanks. Yeah, so it has some nature that's sort of similar to Hodge theory. There's some harmonic stuff in going into it, but that's really all I want to say. Yeah, you can really get quite far with just what I've written on the board. Okay, let me kind of give you a really like. Sorry, I did want to mention one more feature of the theorem before I do an example, which is that so the Higgs bundles corresponding to complex variations of Hodge structure. So this funny condition I wrote down here, which is just some kind of generalization of like coming from the cohomology of a family of varieties, are exactly the E theta, so the Higgs bundles, which are isomorphic. Well, there's something kind of funny. You can, if you have a Higgs bundle, what you can do is you can make a new one just by multiplying the theta by something, right? And it's the ones where that doesn't change the Higgs bundle. Okay. So this is some other definition, if you'd like, of complex variation of Hodge structures. The ones that are preserved by this kind of funny C star action on the specific Higgs bundle. Okay, and it's really this C star action that's kind of analogous to the Hodge filtration. So maybe let me just mark. I mean, there's kind of a fun exercise here, which is like, if you think about what this isomorphism has to look like, or this family of isomorphisms has to look like, you'll see that, so what you'll get is actually a C star action on this underlying vector bundle E. And if you divide it into eigenspaces, you'll get exactly some grading like this. So you can really reconstruct this associated gradient of the connection from a C star fixed bundle, from this data, just by looking at kind of the eigenspaces of these isomorphisms. So in the stable case, these isomorphisms are more or less unique, and so you can really extract this gradient.
I'm sorry, why are they not always isomorphic?
Why are they always isomorphic? Yeah, let's see what happens, right? So we have this E tensor omega 1 is theta, and then we have E T theta, E tensor omega 1. Okay, and you're trying to pick one map here, which determines this map and makes the diagram commute. Right? So I think there's no reason why you should be able to do that, right? So maybe you would put like 1 over t here or something like that, but then if you get what do you get? If you put 1 over t here, you'd get a theta going around this way and a theta over t going around this way. So yeah, so there's some already it's sort of a fun exercise to see that theta has to be nilpotent if there's a way of making this diagram.
Because theta square is always 0.
Yeah, so by nilpotent I mean that there's a filtration on E, so the associated gradient of theta is 0. Does that make sense? So one way of saying a matrix is nilpotent is there's a filtration on the vector space, so that when you get the associated gradient you get 0, and I mean the same thing. I'm going to give you another description of nilpotent. Any other questions about this? So you should think this is some weird data. I don't expect you to immediately like be used to it. So let's do an example. So let's do the example where we're looking at rank 1. So what happens in rank 1? So well, what are rank 1 representations? How am I doing on time? Oh wow, okay. Not doing well, it's okay. Okay, so this is what are rank 1 representations? They're H1x C star, so this is the same as maps from pi 1 to C star. And there's a sort of nice way of writing this down. Well, I mean it's maybe let me just say X is a Riemann surface for now, just make things a bit simpler. Genus G. So what is this? Well, this is like C star to the 2G. But there's another way of writing it, which is it's H1x C mod H1 x Z. I guess. Well, it's a Riemann surface, otherwise there's some piece coming from distortion in H2. Okay, so this is some kind of nice uniformization of this torus. It's obviously very analytic. It comes from these exponential exact sequence. Okay, what about rank 1 flat connections? I claim that this isn't totally obvious, but it just comes from unwinding check cohomology. This is the same as H1 of complex OX star goes to omega 1x via d log. Well, in general, you would continue this a little bit because on a Riemann surface, there's nowhere to continue it. Okay, and what is this? This is the complex Z to. This is the same as the complex Z to OX to omega 1x, right? We saw in the last talk that this thing computes de Rham cohomology. right? So this is, well, analytically it's the same thing, but let me write it as h1 duram x modulo h1 x c, obviously the same thing. But if you think about it more algebraically, you can see these things are different, right? Like if you have a flat bundle, a flat line bundle is a map to the space of line bundles, right? This maps to take x just by sending L nabla to L. In fact, it lands in the degree 0 part, as we said, flat bundles have 0 Chern classes. Okay, and now you can see that this map cannot possibly be algebraic, right? If you view it as a map from here to here, right? Because there's no maps from C star to 2G to a Nonabelian variety. There's no maps from C star, right? Except for constant maps. Yeah. So in fact, if you unwind this, what it tells you is that, well, what are the fibers of this map? The space of connections on a given line bundle, and those are a torsor for the space of one forms. So this is an H0x omega 1 torsor, a principal homogeneous space for this vector space over K 0x. So this is some different structure on the same space, but they still are at least complex analytically the same. Okay, what about Higgs bundles? Rank 1 Higgs bundles. Say Higgs bundles, let's say up degree 0. So what's a Higgs bundle of degree 0? It's a line bundle of degree 0 and a map from L to L tensor omega. There's no flatness condition because there's no omega 2 on the curve. Well, a map from L to L tensor omega is just the same as a 1 form. It's multiplying by 1 form. So what is this? This is Higgs 0x times H0 x omega. And you can see that here, and what do? You just break up H1 duram into H0 omega and H1O. And H1O mod H1z becomes H0, and this is what's left over. Okay, but maybe let me remark, this is really not, this is again not an algebraic map. There's no, typically this torsor is not trivial. So, but you can see that this kind of captures some of Hodge theory. So what is this? This is H1XO mod H1XZ times H0 x omega. And so here you see the Hodge decomposition on H1.
So is this a constant? Is this this global homomorphic platform give you the sort of the connection making? Sort of thinking.
So going from here to here is pretty complicated. So for I mean, there's no like in general. The way you do it here is you take your line bundle L, which has some, and you have some one form. You put the unique unitary connection on that line bundle, and you add on the one. It's a bit, but there's some transcendental. I mean, it's like a really, it's not even a complex analytic construction. It's a real analytic construction. Okay, so let me kind of say what the general picture looks like that generalizes this. Yeah. So it is not complex analytic. Yeah, and it is a. Yeah, it's even real analytic, but it's not complex analytic. Okay. Okay. So what happens in general? So there's some spaces one can define. So MBXR. So I'm going to be a little bit loose about what I mean by here. So this is. Well, as a set, it's the set of rank R semi-simple local systems on X up to isomorphism. So what I really mean here is you take representations from pi1x into GL and R. So that's an affine variety. You just pick some generators of pi1. For each one you associate a matrix, and then you impose the equation that the relations in pi1 are satisfied. And then you mod out by conjugation on GLR. So this is some GIT quotient. It's like an affine GIT quotient. Similarly, you can define M duram XR, which is rank R semi-simple flat bundles. Of isomorphism. And again, you can describe this as just some kind of GIT construction, but let me remark it's typically no longer affine. And we can already see that here, and there's well, it's not totally obvious from what I've written, but this is not an affine directive. Okay, and then finally there's what people usually call M Dolbeau or M Higgs of XR, which is, this is rank R, and I'm going to write some words which you can ignore. Polystable E theta with CI E equals 0. So polystable just means direct sum of stables as opposed to semi-stable. Like a semi-stable thing can be a non-trivial extension of stable things. Okay, and then the statement is that the complex points of these varieties are all homeomorphic. Okay, so in a canonical way. So let me say a bit more about that. So MB XR is complex analytically isomorphic to M de Rham XR. So that's the Riemann-Hilbert correspondence. We saw this yesterday. And then this thing is real analytically isomorphic to M Dolbeau XR. Okay. So this is Nonabelian Hodge theory. Okay, and now I want to maybe make a remark, which is that we now see that there's some sort of very beautiful extra structure, which is there's a C star action on this thing, which I described over there, given by scaling the Higgs field. Okay. So now I want to go back to this non-abelian version of the Hodge conjecture and make it look a little bit, make the two sides of it look a little bit more parallel. And then we'll actually do something. And so far, I've told you a cool theorem, and I'm doing some philosophy now, and then we'll actually prove a theorem. Okay. So let me remind you what the statement of the Hodge conjecture was. So it said that the image of Zi of x to h2i x q of I was exactly the span of h2i x zi, the q span of this, intersected with what I called h00 h2i x q of I. Sorry, so c of I. So this just means hii of this. Okay, but let me rewrite this in kind of a funny way. So if you have a Hodge structure, H is direct sum of HPQ, so let's say this is a complex vector space, there's a sort of funny way of remembering these HPQs, which is you get a C star action on H where Z acts on HPQ via Z to the minus P, Z bar to the minus Q. So this seems kind of like a funny thing to do, but the reason for doing it is that if you have a real vector space with an action by C star as a real Lie group, that's actually the same as a decomposition of the complexification into HPQs, where HPQ is the conjugate of HPQ. It's just because Z to the minus P, Z bar to the minus Q is conjugate to Z bar to the minus P, Z to the minus Q. This is just a funny way of capturing what it means to be a real Hodge structure. Okay, so what is this? In the way I've written things, well, Z to the 0 is 1. Z bar to the 0 is 1, right? So this is the same as H2i x C of I, and then the C star fixed points. Okay. So what was the non-abelian version? So it says that rho is a, so let's say rho, so let me write it this way. So all rho in Mbedi XR Z points, so here, representations with a Z structure. This is a perfectly good variety, this is a perfectly good variety you can define over Z just because GLN is defined over Z. Intersected with M Dolbeau XR C star. So what does this mean? It means exactly that they underlie a variation of Hodge structure. And then the statement is that these are of geometric origin. Okay, so maybe let me just say a word about what I mean here to be really precise. So here I mean rho is a Q representation, but it has an underlying C structure, so it comes from this. Okay, and now you're supposed to think, well, this part is supposed to look like this, and this is the C star with the fixed points, that's supposed to look like this. Okay, so this is some kind of complicated way of making these two conjectures, I think, look, in my view at least, completely parallel. Does anyone have any questions about this? So all we've done here is some philosophy. We've bought ourselves a C star action. Yeah.
So from like this bundle to C star, what you recovered that
That's right. Yeah. I mean, well, from any Higgs bundle you can, or any stable Higgs bundle, you can recover an irreducible representation, and irreducible CBHS carries at most one like Hodge filtration. It's not obvious, but it's true. So yeah. So what this is saying is that from this thing and the fact that it's C star fixed, you can recover the flat bundle with the Hodge filtration.
But even if they probably didn't know that it came from like this construction, like you just start with
Yeah. You start with any C star fixed point. You can make out of it a complex variation and if it's stable, you can do that in a unique way. Okay. So for the rest of the talk, I want to tell you something about the geometry of this space and then use it to prove something cool, which is sort of relevant to what we talked about last time. So this is the next section. It's geometry. This moduli space M double XR. So the cool thing about linear maps is that you can take their characteristic polynomials. And that's somehow the key juice in Nonabelian Hodge theory. So maybe let me just point in this example before I dive into it to what we're trying to construct an analog of. So here, this moduli space of Higgs bundles has a map to a vector space. It maps to H0 X omega. And it turns out that such data exists in general. Okay, so E to E tensor omega is a Higgs bundle. So there's something kind of funny you can do to it, which is, well, you can move this omega to the other side, right? So you get an action of the tangent sheaf on E. Right? And that extends, for formal reasons, to an action of the symmetric algebra on the tangent sheaf on E. Okay. So maybe let me just say a word about this formal reason. So in general, if you have an action of, like, if you have a map from T tensor E to E, you would get a map from you would get an action of the tensor algebra on T on E. But because of this data composed with data being zero condition, it factors to the action of the symmetric algebra. Okay. So maybe let me make a observation. Well, this is a sheaf of algebras on X, which means we can view this E as a sheaf on relative spec of this. So we can view E as a sheaf on the relative spec of sim star X. Well, what is this? This is the total space of the cotangent bundle of X. This is just unwinding the correspondences between modules over a sheaf of algebras and coherent and quasi-coherent sheaves on the spectrum of that sheaf of algebras. Okay, so I want to make this explicit and tell you why it's useful. Okay. So the question I want to ask is, well, what is the support? And if you just pretend E is a vector space with a linear map from E to E tensor, let's say another vector space, you'll see that the answer should be controlled by the characteristic polynomial of this linear map. So if you have a map from E to E, if you view that as a sheaf on the affine line, the support of that sheaf is just cut out by the characteristic polynomial of your linear map. The same is very characteristic. So maybe let me make a definition. So AR, the direct sum from I equals 1 to R of H0 of X with coefficients in sim I omega X. So if you have a map like this, the coefficients of the characteristic polynomial are going to be valued in the symmetric powers of omega. So let me explain that now. So how do you take the characteristic polynomial of a Higgs field? Does it map from n below XR to this affine space AR, which I'm going to call H, it's called the Hitchin map, which sends E theta to the trace of wedge I theta. So just like the coefficients of the characteristic polynomial are the traces of the wedge powers of a matrix, there's something a little subtle here. You have to think of this as a map from wedge I E to wedge I E tensor sim I. A little bit of subtlety here. It may be easiest to think about when you have a curve, and then, well, you should think there's a canonical isomorphism between wedge I of E tensor a line bundle and wedge I of E tensor the ith power of that. Just write things down in a basis, we'll see what's correct. And the claim, which unfortunately I'm not going to have time to prove, is that the fibers of this map correspond to E theta supported on a fixed subscheme of total space of omega, which is finite flat over X. And the subscheme is called the spectral variety. Let me just verbally say what's happening if X is a curve. So if X is a curve, this is a line bundle. So locally you can trivialize the line bundle and you just get a map from E to E. That map has a characteristic polynomial. And what are you doing? You're looking at the zeros of that characteristic polynomial. Now if you have, if you're at a point of the space corresponding to the zero of the characteristic polynomial, there's a natural vector space corresponding to that point, namely the eigenspace of this operator corresponding to that eigenvalue. That's the zero of the characteristic polynomial. So here you think of this support as the set of eigenvalues of this map, and then you have a sheaf on that support, which is the eigenspace for those eigenvalues. And that's how this corresponds. Okay. And then maybe let me make two observations and then quickly use it to do something. So the first observation is that H is proper. So this is not obvious, but it follows by identifying these fibers as moduli spaces of sheaves on these supports. So each fiber is a space of sheaves on a fixed variety. You identify it with a certain moduli space of semi-stable sheaves, and those things are automatically proper. Okay. And the second fact, and this is really beautiful, is that the limit as t goes to 0 of E t theta always exists and is C star fixed. Okay, so why is that? Well, what happens when you act by C star on this space? If you stare at a little bit, what you're doing is you're just scaling this to 0. So you take a point here, you scale to 0 over here, but this morphism is proper. So the fact that the limit exists here, 0, implies the limit exists here. Okay, and then it's formal once the limit exists, and it's C star fixed. Okay, so what this tells you is the following beautiful fact. Any representation, let me say it's semi-simple, although that's actually not necessary, can be deformed to a CVHS. That's a kind of very deep result about the geometry of algebraic varieties. Okay, let me now quickly use it to do something a bit more concrete. So. Yeah, go ahead.
This limit like E, T theta equals to 0. It doesn't like convert to E, T.
Yeah, that's right. So the reason why is that E comma 0 might not be a semi-stable bundle, right? So E comma 0, yeah, might not live in this moduli space, but it converges to something in this moduli space. Yeah, you can kind of algebraically compute this limit, though. It's not so. Okay. So let me state it. So this is. Let me just say something now about rank 2 local systems. So I want to use all this geometry to explain at least a little bit about the proof of a very important theorem. So this is a theorem of Corlette-Simpson. So they prove something in the quasi-projective case, which it's not really any harder than what I'm going to say, but it's a bit more involved to write down. So I'll just write it in the projective case. So X over C is smooth projective, and V is going to be a Zariski dense SL2C local system on X. Okay, what do I mean by that? I just mean the monodromy is Zariski dense in SL2C. Okay. Then one of two things happens. So there's a complete classification of these. So either one, there exists some X to Y, with Y a smooth Lee-Mumford curve. Okay, so there's a little bit of stackiness here, which you should just pretend doesn't exist for the sake of your sanity. So there's some F like this, such that V is F star W for some W on Y. Okay. So the first possibility is that V is pulled back from a curve. The other possibility is that V is rigid, and in fact, of geometric origin. So what this says is that classifying rank 2 local systems boils down to classifying rank 2 local systems on curves, maps to curves, and rigid local systems. All right, so I obviously don't have time to prove this theorem. I just want to give you an idea of how to see that there has to be some dichotomy with this. So before I do that, maybe let me just say a word. So what do you have to do to show a rank 2 local system is of geometric origin? Basically, you just have to show that it's a sum end of a Z variation of Hodge structure. And the reason why is just because of rank 2, there can only be at most 2 interesting pieces of the Hodge filtration. And then if you have something with only 2 interesting pieces of the Hodge filtration, it comes from a Nonabelian variety. Okay, so what do you have to do? You have to construct a variation of Hodge structure, and you have to construct a Z structure. So the fact that it's rigid means it's C star fixed. So you already have the C VHS part for free. So the hard part of this is showing that if you're rigid, then you have an integral structure. And I'll say something about this from a very different point of view in the next talk. So what I want to just say a word about, so this is going to be a very sketchy sketch, is just so how to see that if it's so V not rigid. What do I mean by that? I just mean it lives in a positive dimensional subvariety of the moduli space of representations of MB. So I want to say if it's not rigid, it comes from a curve. So I just do I have time to say a word about that? Yeah. Okay. Okay. So okay. So what is this? What does it mean that it's not rigid? So V lives in M-Betty of X2, and it actually lives in some spec R, which is positive dimensional. Okay. So this is some kind of affine variety. So any component is affine. I'm just going to take this affine component. Okay, but now I claim. So I claim that the image. So if you look at the image of this component, let's call this Z. So the image of Z inside of M Dolbeau in the Higgs moduli space cannot lie in the fiber of the Hitchin map over 0. sorry, Z is this component of the Betty modular space image fiber. So it can't live in the 0 fiber. Why? Well, because this thing is proper, right? So you can just take the closure and then you get some proper component, which it would live in, but there's no proper subvariety of, I mean, there's some little lie there. Really what you should do is you should take a curve in this component which doesn't extend to the boundary, and then you can see that's impossible. If it lives in the same notation for 0, you could take the limit at the level of Higgs levels, and then you'd get a limit at the level of representations. Okay, so this can't live in the 0 fiber. Okay, and now, so modulo some mild technicalities is some map from pi1x to GL2R, and then our representation, so the monodromy of V factors through this to GL2C. So this is what it means to live in a component here. Okay, again, when I say mild technicalities, really you should, instead of working with M-Betty, you should not quotient by GL2 and not GL2. Okay, so it's enough to show, let me call this rho R, so it's enough to show that rho R comes from a curve. So I just want to say where that curve comes from. It's sort of an amazing construction. So let's pick a very general C point of spec R. Let's call that rho prime from pi1x to SL2C. I think, sorry, I wrote GL2 here, I should have SL2 everywhere. So because this is very general, the image of rho prime is equal to the image of rho R. So the locus where the image changes is some closed subvariety, some countable union of closed subvarieties. Okay, so again, now it's enough to show that this rho prime comes from a curve. Okay. So rho prime has some Higgs bundle E theta associated to it with, well, what does it mean that it's an SL2 representation? It's going to mean, shouldn't be obvious, trace theta is 0, and det theta is non-zero. Here, the determinant of theta here, this is in H0x sim 2 omega. Okay, so let me say why this is. So this is just the fact that you're in SL2. So Higgs fields work like Lie algebras, basically. The fact that you're in SL2 means trace is 0. The fact that the det is non-zero, it's just because we are not containing the 0 fiber of this map. So here this map is the determinant. Okay. So now, what is the spectral variety? So the spectral variety inside of Tx is just the space of square roots. Of det theta. Okay, so in particular, it carries a canonical one form. Namely, well, if you take the space of square roots of something, then on that space, you get a square root. So it carries a, well, with desingularization carrying a canonical one form. So let's call it desingularization Z tilde. Okay, now here's our curve. So you take Z tilde, it has an Albanese map to an abelian variety. Well, any one form is pulled back from the Albanese. And now this goes to some A, which is the smallest quotient by an abelian subvariety. From which omega is pulled back. And the claim is that the image of this map is a curve. So let me say just a word about why that's true. Because I'm way over time, I'm going to stop after that. So first of all, I claim anywhere where omega is 0 has to go to a point. That just follows from sort of the behavior of pullback of one forms from a billion varieties. So what that means is that if the image is not a curve, you can find a curve in Z tilde on which omega is everywhere non-zero. So in other words, this Higgs field has no 0 eigenvalues along that curve. And what does that mean? It means that the spectral variety Z is atal over the curve. Okay, so if you unwind everything I've said, it means this Higgs bundle is pulled back, is pushed forward from a Higgs line bundle on a double cover. Right? And in particular, the monotomy can't be Zariski dense in SL2. It has to be dihedral. Okay, so this is sort of where the curve comes from. So okay, I hope that convinces you. This lets you do actual mathematics. And yeah, let me stop there. I have much more to say, but
So I guess you can phrase the Hodge conjecture in purely algebraic terms using algebraic cohomology, right?
So I don't think so, right? So there's this part of the Hodge conjecture says that there's this singular cohomology that you need H1xz intersected with some piece of the Hodge filtration, and H1xz is not that's a complex analytic invariant.
Well, I guess even then, so this is complex analytic, but your non-abelian form of the Hodge conjecture sort of passes through this real analytic implication of these moduli spaces, right?
No, but that's also a feature of the Hodge conjecture, right? So to pick out HPP, or the way I wrote it, H00, you need to use complex conjugation, which is not a holomorphic object. Yeah, so I think really it's a complete analogy. I think there's no, I think there's one part I don't really like about the formalism, which I tried to elide, and I think I did so in a correct way, which is that the integral Hodge conjecture is false, right? But the way I wrote things, I had this MBXR of Z. But what I really think you should say is that if you have a Q local system with an underlying Z structure, then it's of geometric origin, and that's the analog, like a given Q local system in principle, and multiple underlying Z structures. So I think that's sort of the comparison to the failure of the integral Hodge conjecture. I don't know, all these things are so conjectural that I don't really have a strong feeling about what's supposed to be true.
So the C-star action is only act on this Higgs bundle model space, but
Yeah, so the action is holomorphic only on the Higgs model.
and it's not on this round.
Yeah, and you have a complex analytic action. Sorry, real analytic action on the ground model.
So can I think about this Higgs field?
Yeah.
Some sort of first order approximation of the connection matrix of the.
I think no. I think it's more complicated. So in particular, in general, if you have a flat bundle, the underlying vector bundle of the corresponding Higgs bundle can be different, and you actually already see that for CVHS, right? You're taking the associated gradient of some filtration. So I think it's I don't really know of a simple. I mean, I don't know of a description except for writing down the definition of a harmonic bundle. It's some kind of complicated real analytic thing. Yeah, I don't know if that is. Other questions?
So here you said there's like a positive dimensional family information for your
Yeah.
and somehow you pass it to the L2 under and then you said it's not in the
zero
diagram. Why was it not in the
Yeah, so the point is that this is affine. So what you can do is you can pick a curve in this going off to infinity. So in particular, some family of irreducible representations with no limit, right? But if in here, and that makes sense just in topology. Okay, I'm taking some sequence of things that doesn't have a limit. So now I pass through this homeomorphism, I get some sequence of things. If they live in this compact subvariety H in sub 0, they would have to have a limit point. Yes. Yeah, that's a good question. So there's some results of Jost and Zuo where I think they which I should say I'm not 100% confident about the status of, but I believe the statement is that you're either rigid or pulled back from a variety of dimension less than the rank of your local system. But I don't understand how the argument is supposed to go. I think it's, so here really the geometry of the spectral variety was very simple because you were just extracting square roots of something, but if the characteristic polynomial is more complicated, it seems very hard to analyze to me at least. Yeah, but yeah, I'm agnostic about that statement. We're recording this, so sure. Maybe we can clip the.
All right, take two.
Oh yeah, I can say a word about this. Okay, so let me just say two things. So first of all, there's yeah, what else would I say if I had an unlimited amount of time? Is what Stefan asked. So first of all, there's some. So if I explain why you're in this setting or this setting very loosely, and there's much more to say about descending from the spectral variety to X. But in this setting, there's more of a claim than rigidity. There's an integrality claim. So I'm going to say more about that next time from a very arithmetic point of view. There is a proof of integrality from this sort of Corlette-Simpson point of view, where there's some analog of this whole story in the non-Archimedean plural. So the other thing I was going to say is that, so I want to try to connect some of this stuff to what I discussed last time, namely understanding if you have a family X to S, you get this moduli space in you get a families of all of these moduli spaces. And we actually saw that last time. So if this family was, you know, a bunch of punctured P1s over the configuration space of points in P1, we get this non-abelian Gauss-Monin connection, which is really a structure on this de Rham moduli space. And so maybe let me state a theorem, which I was going to sketch the proof of again, using some of these non-abelian Hodge theory techniques, and in particular the fact that you can always deform to a variation of Hodge structure. So this is a theorem joined with Aaron Landsman. Again, just about n-tuples of matrices, if you like. So there's an action of pi1 mgn on representations of pi1 of a genus G Riemann surface with n punctures. And the theorem is that, sorry, let me, so if rho is a representation, such that two things happen. So first of all, the rank of rho squared is less than or equal to G, if the rank is small compared with this genus, and two, rho has finite pi1 mgn orbit, then rho has finite image. So this was some question of Kissen. And it really uses this deformation to a CVHS. So maybe let me just say a word about why you should care. So this was in the background of my previous talk too, and I'll talk a bit more about it in the next two. So this thing where you have a family of varieties over some base, and you study the action of pi1 base on the base of the representation, is some kind of geometric version of this notion of arithmeticity that Sasha discussed in this talk. So, and ultimately, you know, Sasha proposed the goal of trying to classify geometric local systems, and I think that's too big a goal to try to you know, at least for me to believe that I can say something useful about. But at least in some special cases, like so for example, for a generic curve, it feels kind of doable. And so this is meant to be some kind of very, you know, some kind of approximation to that goal in some settings. And so I just wanted to point out, you know, there's some kind of interplay between this sort of non-abelian Hodge theory, which goes into this proof, but also things that I'll discuss in the next talk, going into this theorem, which really have an origins in like the Lennox program and arithmetic. I would have said a word about this, and now I have to.
Great. Well, maybe we'll reserve any other questions for lunch. Do you think we should like start 10 minutes later? Yeah. We can start at 1:40 instead of 1:30.
So this is